Sam Kottler. I work at DigitalOcean. That's my Twitter thing. Just some background. Yeah, as Seth said, I manage the platform engineering team at DigitalOcean. I used to work at Red Hat on Vert stuff. And a lot of the stuff I'm going to be talking about today is super relevant because we use a lot of the techniques I'm going to be talking about on Ruby core security to keep the Ruby runtime secure. And I've also kind of contribute heavily to a bunch of open source stuff. Anyways, like the TLDR is that my job is basically to debug really weird system stuff, including like firmware and vendor stuff and all of that. But today I'm going to be talking a little bit about kind of a combination of process and tools. Some of the tools you almost certainly know, and some of them you might not be as familiar with. But I think this balance of kind of having process and tooling produces good results when we're debugging systems and software. So software is pretty terrible, in case you didn't know. A huge part of the reason that I think software is bad is because we have bad foundations, right? So you go and you look at some of the issues that we're finding in super prominent open source systems like OpenSSL, glibc, the Linux kernel, other kernels. As you look across the entire stack, the story of those projects tends to be pretty poor. OpenSSL, for example, is maintained by one person who's not paid to work on OpenSSL. And the result of these bad base systems are bad systems that run on top of these bases. And this isn't to say, software is terrible. It's more to say we have bugs, and when we find bugs, we need to fix them in a systematic way, not in a way that is more kind of, I guess, loosey-goosey. We really want to be able to solve the problems in software in a way that provides us a working basis to solve similar problems in the future. As I said, operating systems are a huge reason that we have this problem. I'll talk a little bit more about this, but I think a huge part of what the operating system provides today is utterly unimportant. And if you look at things like unikernels and rump kernels, we're starting to see that the operating system is probably going to basically go away in the future, to be replaced by something that will be smaller, more compact, and obviously lower surface area means less bad software. Another huge reason that I think kind of operating systems are this pivotal point in where bugs lie is because obviously the kernel is this like critically important intersection between kind of obviously user space and the hardware that runs underneath, and the bugs and the kind of stuff that you see at scale are not isolated to software. Vendors and all kinds of different conditions lead to interesting problems in user space. So I'm going to kind of talk about some of those problems and riff a little bit about some of the more interesting stuff that I've run across recently. But the fundamental thing that makes debugging hard and understanding systems hard is that verifying correctness on a moving system, right, on kind of a system with entropy is incredibly difficult. As the system changes from underneath you, it's challenging to understand what is going on and why it's happening. So if we look at the kind of basis of a lot of these kinds of correctness issues. So I'm not talking about correctness like software correctness. I'm talking about like verifying that something works in a reproducible way. It becomes increasingly challenging the lower you get because like atoms and stuff, like science happens, which is hard. So as we kind of build these systems, as they change, and as you have to debug a moving system, it becomes incredibly challenging. And the problems, as I said, don't exist only in software. They exist in like runtimes and then libraries that those runtimes rely upon, drivers, kernels, devices, hardware. Basically all this stuff has a ton of different and kind of unique problems. For example, a great unreliable hardware story is when I was at Red Hat, we debugged a huge amount of, well, we spent a huge amount of time debugging why guests would crash under a certain condition. Turns out, like, Intel sent us, well, whoops, a vendor sent us some test memory that was missing a pin, which will not work. So, whoops. Anyways, we really have these unreliable base systems that lead to unreliable systems that run on top of them. And for what it's worth, I actually don't think systems being unreliable is necessarily a bad thing, right? It's led to building, you know, we've moved largely, sorry IBM people, we've moved largely away from mainframes onto commodity hardware and built, I mean, I guess you don't work on mainframes, but we've moved largely away from mainframes, which are like, this thing can never go down, these systems can never fail, to commodity hardware that you can get for not a crazy amount of money and build reliable systems on top of by taking the unreliability of those systems and assuming that they're going to be unreliable, and then, you know, that's the basis of the thing that you're building. And that philosophy is a huge amount of what's driving, you know, kind of what a modern application looks like. Distributed systems is a distinct field. It's always kind of been an academic field, but it's now kind of a distinct field as well inside of industry. So the lack of reliability in a lot of these things isn't necessarily a bad thing. It's just a fact of life at this point, and that's kind of, you know, the basis of having to debug stuff is like having unreliable systems might not be the worst thing. It just means that we get to build systems that accept the lack of reliability for the sake of understanding, you know, kind of what we're building, which is kind of cool. Anyways, it's not this bad, Judge Judy. It's kind of pixelated, but it's an amazing GIF. Anyways, bugs are going to happen, obviously, and tools help quickly find and fix them, which means that as we build systems, when we find bugs, we want to have tools. But I think more importantly, we want to have process around utilizing those tools, right? So we need a framework in which to actually build and test fixes, for example. So I basically have like the 5-step debugging process. And the first one is actually the hardest. So, you know, it's incredibly difficult to suspend your disbelief, right? Like, how often do you hear someone say, like, this should never happen, but then it's happening? How often do you hear someone say, you know, I checked everything, this isn't possible, and then it's like, no, it is possible, it's happening. And so suspending your disbelief, stop saying like, oh, it must be here because I saw this other bug that looks kind of like this, you know, getting rid of that mindset is the first step to actually finding, you know, deep bugs. And without that, without the ability to do that and without the ability to remove assumptions, it's incredibly challenging to actually find a lot of these systems bugs. Reproducing the issues. So this is obviously incredibly important, but it's really challenging in a different way, which is a lot of these conditions you don't understand what triggers them, and as a result, you can't fix them because you have no deterministic way to figure out what a fix might be. And then this is actually a really important one, and sometimes produces obvious fixes, which is compare a broken system with a healthy system, right? What changed between here and here? What, you know, sometimes like upgrading a library, especially if you use certain OSs, like upgrading a library, they might just like break ABI and then everything's broken. And so, you know, building a lot of that kind of stuff into the debugging process, right? Taking a healthy system and comparing it to one that's not healthy is important. And then, sorry, figure out what's wrong. This is the meat of the process. But the cool thing about figuring out what's wrong is that once you know what's wrong, it's often really easy to fix it. And so once you understand a system to kind of a full extent, then you can easily go and fix it in most cases. Or, I mean, knowing the problem is better than not knowing the problem, and even if it's hard to fix, it's still good to know that this problem exists. So the rest of the talk will kind of focus on step 4, right? So this one. And these tools that I'm going to talk about, you've probably seen before, but I'll just talk a little bit about what they do, what they're for, and talk a little bit about their place in the debugging process. So as I said, bugs happen, tools can help find and fix them, and let's talk about tools now. So we have a kind of framework of process. Let's figure out the next step. So here we have this really simple Ruby program. It prints a string. It requires another file, and then has the string method on the derp module in the derp class. And so when we do this, that file doesn't exist, but the runtime tells us that it doesn't exist. So it's cool. But what's actually going on under here is we're obviously we're making system calls to open files, and here's the strace output, right? So this actually shows how weird and jank Ruby's loading system is, but basically TLDR on this is that we're trying to find a file, we build a path for library support, we then check that that file doesn't exist, and then we return this error back to the user, which is all well and good. But basically, you can see here all of these different kind of interactions are system calls. So if you're not familiar with the kind of interface between userspace, which is like your command prompt and all the applications that are running on your system, and the underlying kernel, this is how the things that are happening in user space, like you running, Ruby derp.rb or test.rb, then results in things getting, processed inside of the operating system, right? So you can see we open a file, we stat some other files, we close a file. What do? We set some UIDs, group IDs, whatever. This is all just kind of minutia, but the thing is, this strace output, although you wouldn't really use it in this specific case, is incredibly useful for looking at a system and introspecting what is actually going on there without having to know how a language works. So, in Ruby's case, this was pretty obvious. It couldn't load a file, but what if there's a memory leak, or what if there's, weird behavior and you don't understand what's going on, or you just don't know language well enough, but you know how to read strace output and know system calls. This is a great way to be able to kind of work on that. And reading strace output is actually really easy. Like, this looks intimidating, but inside of here it's fairly simple to read, right? So you have like fstat 5, some arguments, and a return value, which is 0. So we're file statting on file descriptor 5, right? And then arguments. So the thing here is that when you have all this output, it's obviously super intimidating to dig through, especially like this is not a lot of strace output compared to like running strace on like a heavily loaded system. But when you have kind of all this output, it's pretty intimidating. But I mean, the thing to search for is like, depending on what kind of system you're running, you can like, searching for the string error is a really easy way. Like, systems often return this stuff, you just don't know about it and you don't know where to look, right? So as we break this down, you have a function, which is a system call, a file descriptor. If you run something Unixy, you can find all the file descriptors in /proc, and you can even like read their environment out of /proc, the arguments, and then the return value, right? So here we fstat file descriptor 5 with some mode settings, and we get 0 back, which I think in fstat's case means that the file doesn't exist. So basically, reading this strace output is not incredibly difficult, right? It's just finding the thing inside of strace to kind of look into. And this stuff isn't super complicated. It's just a matter of digging and digging and digging. And, you know, reading strace is a great way to just like hop onto a foreign system that you have no knowledge of and kind of dig in that way. It's not super challenging either. It just looks scary. One thing I will say is, like, if you don't run strace on production systems, you'll have a bad time. Actually, one of the interesting things that Linux 4 has, if you run Linux, if you run Solaris or FreeBSD, like, you have dtrace already, you're already in a happy place. But Linux 4 added a dynamic tracing framework that will enable something like dtrace, which is basically no overhead introspection into systems. So there's a ton of interesting work happening in Linux finally to get Linux up to snuff with what Solaris had in 2001. So feels good. Yeah, so system calls are a unified interface to debug user space, right? It's the one thing you see everything that's going on, and as you look at that kind of output, you can really quickly understand what's happening on a system, especially because no matter whether it's Ruby, Python, whatever language you use, whatever daemon you run, even if you don't know what it's actually doing, like, you can very quickly find out what's going on. So next I'm going to talk about debugging a crash. You see SIG/SEG-V, and it's going to be a sad day, and knowing what to do next is actually often the hardest part, because actually going and reading source code to find a seg fault generally isn't really going to help you. Like, it's not easy to spot a lot of these bugs, and we need tools to help us do it. So here we have a program that's really simple. It has an integer array of 5, and it's allocated, and then we set memory to be a char, and then we return 0, real easy. But when we build it and run it, it will crash, right? Because you're trying to memset on address space that isn't malloc inside of this program, and the sadness ensues. But if we kind of use GDB, we can run this program kind of inside of a tool that will let us help us figure out where the seg fault happened. So here's the program again. You just run GDB list. If you've never run GDB, you get dropped kind of into a shell, it's basically a REPL, and you can run list and see what's loaded in. You do one quick thing is, I don't know actually the LLVM flag, but you run GCC -G, which builds the file with symbols, and then output into the file foo. So here's the program that we have loaded. We run it and seg fault, and this is the least glorious part of like figuring out what's going on, is like, oh, running it and seeing a seg fault, right? But the cool thing is that we see, I'm not going to read that address space, but at some address space in memset, there's a seg fault inside of libc, which is where memset lives. So again, we're doing something we shouldn't be doing here, but as we do that, we can kind of look at where that crash took place, right? So obviously in a super simple program, like when you have this, it's really easy because you have one function. But in more complicated software, obviously being able to get a stack out of a running system is incredibly important when it's seg faulting. And so as we do that, we run where, and we see in memset inside of the main function. Sad, sad. Again, here's a fixed version where we're dealing with the variable that we declared up above. So size of foo is actually a hack here. You probably don't want to do this because like integer size is different on all different types of systems. So if you're on 64-bit, you have an 8-byte integer, you have a 64-bit integer, versus a 4-byte integer, 32-bit integer on a 32-bit system. So the moral of the story here is when you have crashes like this, being able to kind of introspect into them and looking at a stack is how you fix these problems. So obviously, again, dig, and this will probably take a while. Like, even if you know where the seg fault exists, it's incredibly complicated in larger software problems to understand what's going on. But once we have tools, we can kind of start to look at where this is happening. Also, if you have kernel crashes, there's a tool called KGDB, which actually, when the kernel dump happens, k-execs into another kernel, and then gives you a GDB session with the running kernel session inside of it, right? So the kernel that just crashed, you now have that entirely loaded, which is pretty cool. You can obviously also, if you have kernel dumping, you can take that, the core dump that the kernel just produced or kdump just produced and load that into GDB. Problem is, and this is where it gets harder to figure out, is if you have a system with 128 gigs of RAM, you have a 128 gig core file, and it takes like 18 hours to load it into GDB. So KGDB is a great tool in that way, where like you can just hop onto the console on a machine and see what's going on. So yeah, pretty simple fix in this case. Might not be so simple when you have an actually useful program. We run it again, and it ran and exited normally. Sweet. And the last kind of tool that I want to talk about is a profiling tool, but in kind of a different way than you would normally think of. So profiling is normally kind of looking at performance management, right? But in this case, the tool I'm going to talk about here is going to kind of focus more on memory management, which is, if you're doing anything in C, which you probably are, even if you don't know if you are, you definitely are, even if you don't know if you are, is super important. So if we look at the anatomy of a memory leak, I'm going to talk about a memory leak that I found in Redis, actually 482 memory leaks that I found in Redis. But if we look at a memory leak, we get to kind of look at the worst of why we shouldn't manage our own memory. But regardless, as we look at something like redis-server, right? So you have a data structure server like Redis. These tools are obviously constantly allocating and freeing out of the memory pool on a system. But as you kind of handle that, you have the potential to leak memory. So I'm actually going to circle back on the Redis thing and talk about this program, which is you have a function called f. It mallocs. In this case, this is on a 32-bit system, so integers are 4 bytes, 32 bits, and it will malloc, obviously 10 times 4 is 40, and then you have your setting, in this case, the 11th item in an array to 0, and then you call that function, right? So super simple, but this has 2 problems. So again, build it with GCC and then run it under a tool called valgrind. I think valgrind's a little bit less of a well-known tool than GDB and strace, but it's incredible. It's basically a correctness checker, but it has this -- leak check equals yes, which is incredibly useful for finding leaks in all kinds of software. Run your favorite database under this. You'll get a lot of false positives, but you'll also find actual memory leaks. In this program that I showed, this obviously returns 0, so it's not particularly important that you just potentially leaked memory, which I'll show. There's a leak in this program, but it is important if you have a long-running daemon. It's actually interesting. The intersection of these 2 problems is kind of cool because so GitHub a while ago moved from, I guess they had some kind of internal Git implementation to running the actual Git binary, and the Git binary is obviously not a long-running daemon, right? You run it once and then it exits, but they started finding like all kinds of memory leaks in Git, which is cool because they got fixed. They don't do that anymore. They use libgit, but there's all of this stuff that you can find, even in simple programs around correctness by running valgrind. So again, so there's, it's called heap.c. There's a heap problem here as well. But we run valgrind ---- leak check equals yes, and then run the heap program, right? So we're basically using valgrind as a shim between the program that we're about to execute and valgrind itself, so that valgrind can actually inspect all of the memory that gets allocated and freed and look at the running program. So we run this program and we get, this is 2 errors. They're not very distinctly separated, but the first one is invalid write of size 4, which means we have 4 bytes that are, as you can see here, 0 bytes after a block of size 40 allocated. And then the second one is actually this, which is there's a memory leak, right? So if we look in this bottom part, in the heap summary, we allocate 40 bytes in one block. There's 1 allocation, 0 frees, 40 bytes allocated, and we didn't free those that allocated memory at the end, right? So we ran it under valgrind, and we lost 40 bytes of memory. Again, not a huge deal in this case because the program just exits. But if you're running a long-running daemon, obviously leaking memory is not super great. So let's look at how knowing this helps us fix the problem. So the first issue is invalid write of size 4, which means we don't have memory allocated that we're now writing to, right? So just, obviously we're starting from 0 inside of that integer array where we have allocated 40 bytes and it's on a 32-bit system. So as I said before, 32 bits equals 4 bytes, you divide by 8. And then if you look, you see that we're allocating the 11th byte in the array, right? So we're trying to allocate from byte 40 to byte 44. Clearly that won't work because we haven't allocated that and problem ensues. This actually will generate a compiler warning, but if you look on any large project, they have a lot of compiler warnings unless the maintainer of that project is crazy about compiler warnings. But there's a ton of issues around this because you're now trying to utilize memory that you haven't allocated. Clearly, we could either change that to 11 up above or change down below to 9, but either way, we need to be operating inside of memory that we have properly allocated. So the second thing that we talked about was that there's a memory leak, right? So if we go back to the original program, we allocate 40 bytes, and then we return 0 after the function runs, and we set, obviously that broken thing that we just talked about. We now have 40 bytes allocated to this program that we never free. There's no free call here. So now if we add a free on x, which is the integer pointer array, then we can actually rerun valgrind and no problems detected. So these are just a couple of the different tools that we can use. But again, process is the most important thing here. So suspend your disbelief, reproduce, compare the broken system with healthy systems, figure out what's wrong, and then fix the problem. That is all I've got. So we have some 10 minutes-ish for questions.